Our planet, this remarkable blue sphere teeming with life, is governed by forces both seen and unseen. We witness the power of the wind as it sculpts sand dunes and the relentless energy of the ocean as it carves coastlines. Yet there is another force, one that is profoundly fundamental, utterly silent and completely invisible. It is a constant companion in every moment of our lives. This force holds the very atmosphere we breathe close to the earth, guides the gentle fall of a single raindrop, and dictates the grand celestial dance of our moon in the night sky. It is, of course, gravity, but gravity is not as uniform as we were taught. To truly appreciate the wonder of its variations, we must first pause and consider what gravity is. In the simplest of terms, gravity is the natural force of attraction between all things that have mass or energy. The more mass an object has, the stronger its gravitational pull. From our perspective, Earth is immensely massive. Its mass creates a powerful gravitational field that anchors us to its surface. Without it, we would simply drift into the void. Gravity is the cosmic glue, choreographing orbits and holding galaxies together. Every particle in you pulls on Earth, and Earth pulls on you far more. An apple falls downward toward the planet's center. Newton unified the fall of the apple and the orbit of the moon with one law. We learn g as 9.8 meters per second squared, a reliable benchmark for engineering and flight. But Earth is no perfect sphere. It bulges at the equator and its materials are unevenly distributed. The notion that gravity is not the same everywhere is wonderfully disruptive. A hypersensitive scale would show your weight changing around the world by tiny amounts. You weigh slightly less atop a high mountain because you are farther from Earth's center. Curiously, weight also changes where elevation barely does. These deviations from a smooth Earth are gravity anomalies. Positive anomalies suggest extra mass. Negative anomalies, a deficit. They reveal denser rocks, crustal thickening, or lighter materials, thin crust, and even ancient buried events. It's a hidden topography of mass as varied as surface mountains and valleys. The ground becomes an active participant with a complex inner story. Every feature leaves a faint but detectable gravitational signature. Mapping them gives us a new sense, seeing through rock, clues to the forces that shape continents and drive Earth's evolution. Long before satellites, dedicated scientists measured gravity on the ground, armed with patience and sensitive tools. A pendulum's period betrays the local strength of gravity, slightly faster where gravity is stronger, slower where it is weaker. Tiny discrepancies hinted at a deeper truth. Gravimeters were delicate, affected by temperature, vibrations, even tides, as teams hauled them across Earth. Each measurement, a hard-won piece of a global puzzle. Slowly, an invisible landscape emerged, gravity's hills and valleys. In India, plumb bobs near the Himalayas were deflected less than expected. It seemed the mountains were lighter, or something counteracted their pull. This mystery sparked isostasy. The crust floats and mountains have deep, less dense roots. Like icebergs, most of their mass is hidden beneath. Few anomalies are as vast and enigmatic as Hudson Bay. Across thousands of kilometers, gravity here is weaker than average. You would be ever so slightly lighter, imperceptible, yet measurable. A profound signal of something immense in Earth's past. During the last ice age, a colossal ice sheet weighed this region down. Like a thumb in a soft ball, the crust dented and mantle flowed away. When the ice melted, the mantle began a slow rebound. Even after 10 millennia, a mass deficit remains, producing today's negative anomaly. Deeper still, slow mantle convection can tug plates downward, removing mass from below. The likely cause is a blend of lingering ice age effects and dynamic mantle flow. Hudson Bay's weak gravity is Earth's long memory made visible, a window into a restless interior. Ground surveys were painstaking and incomplete. Spaceflight transformed gravity mapping by tracking satellite paths. A satellite speeds up over stronger gravity, slows over weaker regions. Early missions sketched the big picture. Breakthrough came with grace, twin satellites measuring their separation. They sensed distance changes smaller than a human hair. As gravity varied below, the satellite's spacing subtly danced. From these tiny shifts, a detailed gravity map emerged. Grace and Grace Foe revolutionized how we monitor Earth. They mapped geology and detected how gravity changes over time. Weighing ice sheets and tracking water, direct planetary-scale insight. Gravity, measured from orbit, became vital for understanding climate and water. These variations are minute yet immensely informative. They are fingerprints of powerful geological processes. They reveal structure, composition, and dynamics of Earth's interior. They help complete our picture from core to crust. For geologists, gravity maps are planetary X-rays. They outline plate boundaries, hidden basins, and crustal thickness. Combined with seismic data, they reveal hot plumes and sinking slabs. We better grasp the engine of plate tectonics, earthquakes, volcanoes, and the shape of continents. By weighing regions monthly, we monitor climate impacts directly. Data shows staggering ice mass loss, fueling sea level rise. We detect aquifer declines in key agricultural regions. These measurements help safeguard resources and communities. Gravity anomalies reveal a dynamic, mysterious planet. Beneath our feet is a complex mosaic, billions of years in the making. From ancient ice to hidden roots, subtle variations tell of constant change. Earth is alive, its metabolism churning deep within. Our sentinels in space give us a new sense to perceive the invisible. We map the invisible, weigh ice from orbit, and track hidden water. Each dataset solves old puzzles and reveals new ones. What other stories are written in the language of gravity? Ancient impacts, lost continents, clues to Earth's formation, still waiting. The deep interior remains as challenging as the farthest cosmos. Its rhythms span millions of years. We capture fleeting snapshots. When you feel the ground, imagine the vast, complex world beneath.